Okay, thank you. All right, so let's continue this discussion on path constraints. So today I want to talk a little bit about the case of state inequality path constraints. All right, now this is somewhat, in some ways it's a little confusing, in some ways it's not terrible, but it doesn't, it's not that easy to deal with these, so we have a state constraint of the following form. So we have a path constraint of the form C of x of t and t is less than or equal to 0. Now I'm just going to do this for a scalar constraint and a scalar control. So assume that C is a scalar function and that u of t is also a scalar function. Because if you have multiple controls, you can repeat the process, or multiple path constraints, you can repeat the process over again for those, so it doesn't really change much. Now, you know that, so a priori, we do not know if the constraint C of x of t and t will be binding. When I say binding, it's another word for saying active at the optimal solution. So that creates a conundrum in and of itself, right? Because ahead of time, you don't know whether this constraint is going to be active. If it's not active, it's as if it's not even in the problem, right? So you have to make some assumption. So what we have to do is, so it is necessary in some way, or it is useful, I should say, rather than saying necessary. It is useful to know something about the activity of the constraint. So what we're doing here is we're saying, well, we don't know this, right? So generally speaking, what people do is they say we assume that there exists a segment T1 to T2 where C of x of t and t is equal to 0. Okay? So that picture looks like this. I've got something on T0 to Tf. There's the value 0. This is a plot of C as a function of t. And here's 0. And there's going to be some segment where this constraint is going to wind up being active, and then some segment where it's not going to be active. So here's T1, and here's T2. Yeah, of course, it's a big assumption, right? I mean, you don't know whether that's actually going to be the case. It could be that it comes up, hits it, comes off, hits it again, comes off, hits it again. You don't know how many times this is going to happen, right? See, but you have to make some kind of assumption that this is the case. Now, just assume for the sake of simplicity here that there's only one such arc where that happens, okay, where it doesn't happen multiple times. Now, if you look at that condition, you say, well, all right, if that's true, then what we can do is we can say the following. We know that, so because C of x of t and t is equal to 0 on t in T1, T2, then the following must be true. That all the derivatives, dc, dt, d second c, dt second, dq minus 1 C dt q minus 1, and then all the way down to dq c dtq. These all have to equal 0, right? But now assume that these first derivatives, these derivatives here, that the control does not appear in derivatives 1 through q minus 1, right? So if I take q minus 1 derivatives, it doesn't appear, but the control appears here. The control appears in qth time derivative of c. So what we can do is, because that structure is known, that we're going to hit this constraint, we're going to write it, and we're going to come off, we know that at t equals t1, the following must be true. That dc, dt, well, all of these must be true. C of x of t and t has to equal 0. C dot of x of t is t1. And t1 has to equal 0, all the way down to c q minus 1, that's the q minus 1th derivative, of x of t1 and t1 has to equal 0. So what we've done here is we've said that these derivatives are not a function of the control. They're purely a function of the state, right? Because I said the control doesn't appear in any of these derivatives. So when I evaluate these derivatives, I am not going to get something that's going to be a function of the control. These don't tell me anything about the control. They're going to tell me about the state. These right here are what are called tangency conditions. And if you look at the form of this path constraint, the derivatives have to be 0 here, because this constraint is going to be, there's going to be some level of smoothness, assuming the functions themselves are well behaved and everything on those derivatives. So at the entrance to the path constraint, we're going to get these derivatives. Then what we do is we replace the original inequality path constraint with the equality constraint that d, I'll just put a q here, c q of x of t and t has to equal 0, where t is an element of t1 to t2. Now, what that means is that I am making an assumption that this constraint will be active at this point. I don't know when. I don't know when the activity starts. At this point, I don't know when the activity starts, but I know it starts at some point t1. I also know that at the state and the time at that point have to have the condition that the constraint and all of its derivatives that don't depend on the control are all going to be 0 at that point, because the path constraint itself is going to equal 0 at that point. So this gives me an additional set of conditions that I can apply. So look what I've done here. What I've done is I've taken the optimal control problem, because so far the rest of the optimal control problem stays exactly the same. I've taken the optimal control problem and I've added a set of interior point constraints, right? Because now what has to happen is that if you look at the trajectory sort of qualitatively, right? Let's just look at x of t versus t. So here's t0, here's tf, right? And here's t1 somewhere here. What it says is that the state has to be such that it's got to meet this set of conditions at t1. Right? What are these conditions? The tangency conditions are met at t equals t1, right? So that is a set of algebraic conditions on the state and time that need to be met in order to be able to determine what's called the entrance to the constrained arc, because the constrained arc starts right here, right? This is the start of the constrained arc. Now, problem with all this is you still don't know whether or not whether this is going to happen more than once. You don't know when it's going to happen. All of these things still create problems. It's not like you've allowed yourself you've given yourself more information about what's going on now than you had before, because before you just had an inequality path constraint and there was nothing in here that provided any insight as to what the conditions were at the point where that constrained arc starts, right? So this is all this provides for you. It doesn't give you any more information. This is where now if you start looking at this in terms of methods for solving optimal control, see there are two things that have to work in conjunction when you solve optimal control problems. And my experience has always been that students just want to go to the computer and be able to implement things on the computer. Why? Because that's the world in which we live nowadays. Okay? The world, I mean, put yourself, I mean, it's very difficult for all of you to do this. It's even difficult for me to do it because I've been part of this sort of modern world that we live in computationally, just for quite a while myself. But put yourself in a world where you don't have MATLAB. You don't have anything other than somebody is running this giant computer somewhere on campus, and you have to pay for that computer time. Literally have to pay for it. You have to take your wallet out and say, it costs so many dollars per hour, and I need to give you $50 in order to be able to use the computer for 20 minutes, right? $150 an hour, right? And that's at midnight. That's a cheap time, right? During the day, it may cost you $500 an hour to be able to run this computer. You're not going to run the computer unless you're absolutely sure that you have something that's going to be worth doing, right? Because you're not going to fork out that money, are you? Would you just fork out money to use a computer? You would never do this, would you? Because you guys can fire up MATLAB on your PCs or your Macs, and you can run it for free. The only thing it costs you is the electricity out of the outlet, right? And that doesn't even cost you anything if you're at the university. You're not paying for it, right? They're paying for it, right? So you have got premium conditions to be able to goof around. That's what I call it. I call it goofing around, all right? These guys, back in the 60s and 70s who were solving these problems, didn't have these conditions. They had to think, right? What you guys are doing is you're trying to avoid having to think. Well, I'll just have the computer do the work for me. The computer doesn't do anything for you. You tell the computer what to do, and it does what you tell it to do. If you tell it garbage, you get out garbage, all right? So if you're going to go about trying to solve optimal control problems by hook or crook, you're going to get hook or crook solutions. And hook or crook solutions are going to lead to hook or crook designs that are going to lead to things crashing. Planes are going to crash. Bridges are going to collapse. The world is going to come to a catastrophic end because you have a million people sitting in a building somewhere, and you didn't design the building right because you did your hook or crook method using hook or crook MATLAB, and you decided and you got a hook or crook answer. You have no freaking idea whether or not it's correct or not. Bad way to do engineering, all right? If you're going to continue to go down this path, and I bring this up because this is what I saw when I looked at some of your exams, that some of you did not understand a basic principle that running the computer does not replace your understanding of what it is that you're doing. It does not replace it. Look at what I've got here. This is all basic theory. There's nothing in here that tells me how to solve this. How to solve it is a completely separate question. Before I get to how to solve it, I need to know what it is that I'm solving and why I'm solving it. It's the why. You need to get a good understanding of why. Why am I doing what I'm doing? It should matter to you why you're doing what you're doing. And the answer can't be because somebody told me to do it. That is a terrible answer. The answer is because from first principles, this is what I need to know in order to be able to do this. And I got these conditions from some basic theory, which is founded on good, solid principles, right? That is where all this comes from. This doesn't tell me how to do it. If you all are worried about how to do it, you're missing the essence of what's going on here. The how to do it is another issue, right? There are lots of ways to do things, right? I can chop wood by taking an axe. I can use a chainsaw. I can take like a crane with a big ball on the end of it, just whack over trees. I can do all kinds of things, right? I don't care about how to do it. I want to know why you would do it that way. Why would you rather use a chainsaw to cut down a tree than take a ball-peen hammer and start hammering on a tree, right? Well, you know the answer to that question. It's because a chainsaw effectively cuts wood, whereas a little ball-peen hammer ain't going to do me any good cutting wood, right? That's the kind of answer you need to be able to give yourself when you're actually doing something in reality, right? You need to say, this is why I'm doing this. I'm doing this because these are the reasons why this makes thousands of times more sense to do than that other thing over there, right? Because if I do that other thing over there, it's going to get me nowhere, and here's why it's not going to get me anywhere. But in the case of cutting down trees, you can actually understand why, right? Because it makes perfect sense to you that certain things cut through wood a lot more easily than other things do, right? So you have a good answer. You need to have that same kind of answer when you're doing this kind of work. If you don't, then you're just grabbing at straws, and you're doing things by hook or crook, all right? So this does not give me any insight as to how to go about solving this. It tells me what the conditions are that need to be met if I have a solution, which creates a major conundrum. This is a major conundrum, right? Because I don't know ahead of time whether or not the problem is going to be solvable, right? I mean, I don't know how many times this path constraint is going to be active. I don't know if it's going to be active at all. What if I make an assumption that it is active and it's not? Then what's going to happen? So here's sort of a thought experiment, right? I have an inequality path constraint. I don't know whether it's active or not, but I'm going to assume it is active. So I'm going to invoke all these tangency conditions, and I'm going to figure out a time at which this path constraint becomes active, and I'm going to solve for it. Let's suppose theoretically I could solve for that entrance time and that exit time, and I get this entrance and exit time. But the optimal solution, the path constraint, is not active. Now what have I done? What have I done? I've done something. Don't realize what it is that you've done unless you really have a basic understanding of the procedure that you just followed. I said I'm applying these tangency conditions. I'm going to assume that there's some time t1 at which this constraint becomes active, and it's active over some arc from t1 to t2. Now, given that, I'm going to apply these tangency conditions. I'm going to add them into my problem, and now I'm going to solve a problem that says enforce these tangency conditions at some unknown time t1 and have some arc from t1 to t2 such that the qth derivative is equal to 0, and I solve that problem. And somehow I get a solution to that problem. What have I just done? But it turns out that at the optimal solution, that constraint is not active. Now what happens? What have I just done? Does everyone understand the question? Yeah? So what is it that I've solved this problem, right? With all these conditions in effect. And I get a solution. Somehow, theoretically, I get a solution. Some procedure I apply. But it turns out that on the optimal solution, the constraint's not active. So what solution did I just get? I got a suboptimal solution. How would I know that? If all I did was follow some procedure that somebody told me to follow, right, I could be completely wrong, and I may not know, right? So therein lies the problem, is that when you get this solution, you also have to then ask the question, what would happen if I never put the constraint in the problem in the first place? And solve that problem. And see whether or not that problem actually violates the constraint, right? Because if it turns out that that problem doesn't violate the constraint, then I don't need to do this at all, right? So the first thing to do before you get into these questions is you ask yourself, well, what would happen if I didn't have the constraint in there? So here's what would happen. Suppose the constraint wasn't in there. The constraint wasn't in there. Here's C as a function of t. Here's tf. Here's t0. So if C is not in the problem, and the constraint were to be violated, right, then what would happen is I would get something that would do this, right? This is just qualitative picture, right? It's a qualitative picture. I don't have the constraint in there. But if it turns out the constraint needed to be in there, then it would have to be the case that for some value, this constraint function would take on a value greater than 0, right? Because if it wasn't greater than 0, it would never be active. But if it is greater than 0, it is violated, which means that now I would have to consider the problem with the constraint in the problem. But let's suppose that I had a situation where the constraint, without the constraint in there, I got something that looked like this, right? Or let's suppose I take another situation where instead of it looking like this, let's suppose it looked like that. Okay? Now, what would you do if you were actually going to do this in practice? Let's suppose I'm in the first case. So there's the first case. Here's the second case. Okay? So somebody explain to me, if I'm in the first case, what would make sense to do? Now we have to get into the transition from what the solution looks like when it's unconstrained to how I'm going to deal with it when it is constrained. Now what would you do? If I was in the first case, what would you do? Anybody have any idea what they would do? What would they do?
Maybe you could try to impose the constraint.
Yeah, maybe you could try to impose a constraint. You'd impose those conditions over there, right? You'd impose those conditions, and you'd say, well, the constraint got violated here, right? So what I could do is I could say, well, I have a pretty good idea that somewhere around this time value here, this constraint's getting violated, and here it's coming back and it's actually not violated anymore. So this suggests to me, but it's a suggestion, because I don't know that this is actually true, that the constraint has one path along which it would actually be active, right? But if I was in the second case, what it would say is, it actually turns out that it looks like the constraint gets violated, and then it gets violated again. So if I'm actually doing this problem where I'm actually trying to figure out when the constraint is active or when it's inactive, I would actually say in the first case, I might be pretty well off if I just assume it only has one constrained arc, right? But in the second case, I'd have to say, well, it looks like it may have two constrained arcs, right? But the problem with this, and this is where it gets very, very difficult, is let's suppose that it looks like it has two constrained arcs. And then you solve the problem, you immediately impose the problem with two constrained arcs. How do you know it has two constrained arcs? Right? You don't, do you? Right? So what you'd have to do is you'd have to solve the problem with one constrained arc in there and see whether or not the second constrained arc actually still exists when you do that, right? Because it may not actually be that way. It may turn out that it only has one, and then you solve that problem, and now it turns out that it never violates the constraint ever again, and so really the solution only has one constrained arc. So just because it looks like this without the constraint in there doesn't mean it's necessarily going to be that way when you actually solve the problem with that you would have to impose the constrained arc in two, the tangency conditions in two places. You may only have to still do it in one. So the problem with all this is, look at how much I need to know in order to be able to do this. There's so much going on in here, yet it's actually deceivingly a very simple problem. All I've done is I've stuck a constraint that says the state, the function of the state has to be less than or equal to 0 along the trajectory, right? So just by imposing that constraint, I have made it so that I have to deal with this. Now, let's take this one step further. Let's suppose I can't do this analytically, all right? There's no way for me to do this analytically. I have to do this numerically. Now, imagine that you're implementing something like an indirect shooting method, okay? In an indirect shooting method, what's the problem? The problem is that you first got to derive these optimality conditions, right? The optimality conditions in the case where there are no inequality path constraints, or say no path constraints at all, don't involve any path constraints, right? They just involve, I got the transversality conditions on the co-state, I've got my boundary conditions on the state, I've got my optimal control condition, I've got my co-state equations, and I've got my state equations, right? So I've got all this theory that I derived that gives you this two-point boundary value problem that needs to be solved. If I now impose a state inequality path constraint on the problem, look what I've just done. I've imposed a constraint that now has to be incorporated somewhere into those optimality conditions, right? I can't solve the problem without those optimality conditions in there. So my boundary value problem, which up till then was just making a guess at these unknown boundary conditions and integrating forward or backward, becomes a significantly more difficult problem because now I have this constraint that has to be. It's an algebraic constraint that has to be met along the trajectory, right? I can't just, the trajectory just can't go anywhere it wants to. It has to satisfy that constraint. So in addition to having differential equations and boundary conditions that need to be satisfied, I now have an algebraic constraint that may or may not need to be satisfied along the trajectory depending upon whether the constraint is active. My indirect shooting just became really, really difficult to deal with because I have to deal with that constraint. So path constraints make a huge difference in being able to do all this stuff because when you have a path constraint in the problem, your indirect formulation suddenly becomes significantly more complicated than what it was without those constraints in there. And in order to be able to use it, you have to be able to know, you have to know ahead of time something about the structure of your constraints, right? I mean, you can't just say, well, I have this constraint in the problem, and I'm just going to stick it in there. But you have to have some idea when the constraint becomes active and when it becomes inactive, because when it becomes active, you have to impose these tangency conditions. Right? So there are a number of things that need to be taken into account when you actually start doing this. It's not so simple to just take these into account. Now, over the last couple weeks, now let's go about this a completely different way. Okay? Let's imagine that I'm solving this problem using direct collocation. Okay? Now, I'm not going to do an indirect method anymore. I'm going to use direct collocation. You notice that in the direct collocation formulation, what did I do? I took the problem. Now, I was talking about these pseudospectral schemes, but you can use any direct collocation scheme. It doesn't matter which one you use. In the pseudospectral schemes, what did I do? I took the problem. Now I'm shifting gears a little bit here. So let's take the problem using direct collocation, because indirect method is going to create a lot of issues, because I've got to integrate these differential equations, these state-costate differential equations with a constraint in there, and I don't know when the constraint is active or inactive. Now let's look at the formulation using direct collocation. So, and just for simplicity, I'll just write this down with a pseudospectral scheme, because it's just as easy to do it with that as it is to do it with it. So now let's talk about incorporation of path constraints using direct collocation. Okay. So if you remember, like in the direct collocation scheme, suppose we use the Redau scheme. Suppose we collocate using the Redau method. So I've got this Redau method. If you remember, the optimal control problem, when I use the Redau method, my cost is approximated by this function phi, which is a function of my initial state, my initial time, my final state. This is after the discretization. Final time, plus tf minus t0 over 2 times the sum from I equals 1 to n of wi times L of xi ui, right? And then my dynamics, so I'm trying to minimize this, and my dynamics or my algebraic constraints that result from my dynamics are d times x 1 colon n plus 1 is equal to f 1 colon n. I may have a boundary condition that looks like this: phi of x1 t0 x n plus 1 tf equals 0, right? Now, how would I incorporate path constraints into this? I can solve this NLP. I've given you a few examples of how to do it. I can solve this NLP by using some sort of an NLP solver. Let's suppose I now want to add a path constraint, an inequality path constraint. Suppose we now want to add an inequality path constraint of the form. I'm going to be a little bit more general here. C min is less than or equal to C of x of t, u of t, and t, which is less than or equal to C max. Okay, this is in the continuous problem. Suppose I want to add it into this NLP, right? The NLP, this is an NLP, right? This is an NLP. And I want to add that constraint into this NLP. How would I do it? Could I do it?
How would you do it?
Would I add Lagrange multiplier? See? Now it's the difference between how to do it and what you're doing. Why would you add a Lagrange multiplier?
Because we are the path constraints that
But does this problem have any Lagrange multipliers in it? Does this problem has, where's the Lagrange multiplier? Can you tell me? Point to the equation that has a Lagrange multiplier. Where's the Lagrange multiplier? There's no Lagrange multiplier in this problem, is there? Right? The solution has a Lagrange multiplier associated with those constraints, right? But the problem formulation doesn't have any Lagrange multipliers in it, right? When I state the NLP, there are no Lagrange multipliers in the NLP. So now I've said, in addition to satisfying these constraints, I now want to satisfy that constraint in some form. How am I going to do it? And when I show you the result, you'll be like, oh yeah, that's obvious. And I'll say the same thing again. If it's obvious, you should have been able to tell me, right? So what is it about this problem? Does this problem confuse anybody? Or is this problem okay? Have all of you understood these methods now to some extent, looked at my code and understood what's going on? Because I went through the other day and explained the relationship between the NLP and that discretization. Remember, I went through and I told you that there's a decision vector. I showed you how to remap the decision vector to the variables in this form, and then form the equations, and then inputs and outputs. I went through all that detail. All right. So if I want to incorporate this constraint, and you can do this with any collocation scheme. I'm just doing it with Redao just because it's easy to see what's going on with Redao. It has nothing to do with Redao per se. What would I do? What could I do? The answer is really simple. It's not the answer that matters. It's understanding the process. Yes?
I'm really reaching for straws here, but could you just take and tell your nonlinear program solver to just satisfy all those constraints while still not violating this additional constraint? So just factor this additional set of constraints into the process of picking the values for all the unknown variables?
How would I do that?
Oh, well, I see.
That's the question I'm asking. How would I do that?
Yeah, you have to find a way of collocating on the...
Yeah, I have to find a way of doing collocation on this, right? Well, what are the variables in this problem? So what are the variables in this problem?
States.
Yeah, the values of the state discretized at the n Redao points plus the final point, right? The values of the control at the Redao points, possibly T0 and TF if they're free, right? That's all that's in here, right? So what are the values? So if I'm gonna enforce this constraint, where is the only place that I can enforce this constraint? I've discretized, right? Where can I enforce the constraint? At the Redao points, right? So we would enforce the constraint the inequality path constraint at the n Redao points, which would look like this. It would say that, if I string it out, it would be C of x1, u1, and t1. I have to be careful with that t1. All the way down to C of xn, un, tn. All of these have to lie between C min, and C max. Now look at the beauty of what it is that I just did. It may seem so simple that you may not be able to even recognize what it is that's going on. You remember over here that when I'm dealing with this in an approach where I have to figure out what the inactivity of the path constraint is, I have to make these assumptions that there are arcs over which the constraint is active, and I have to figure out where that arc starts, where that arc finishes. I got to apply these tangency conditions. I got to do all this stuff. Look at what happens over here. Over here, all I've done is I've taken this nonlinear programming problem, which has a bunch of constraints associated with it, and I've added some more constraints to it, right? The problem with these constraints is clearly more constrained than the problem without these constraints, right? Now, it may turn out that the solution never hits any of these bounds, right? It never hits C min, it never hits C max, right? In which case, I could just remove the constraint completely, right? But look what I haven't done. I have not required myself to know anything about the structure of the path constraint, right? There's nothing in there that says I need to know when that path constraint is active or when that path constraint is inactive. All I need to know is that there is a path constraint and that I can incorporate it into the NLP. So I have not made the problem from a problem formulation standpoint any more complicated beyond just introducing these new functions into the problem, right? The NLP solver, whatever I'm using fmin-con or I'm using snop, it's going to go about, from some initial guess of that decision vector, it's going to go about trying to figure out what is a point, and a point meaning in this finite dimensional space, that satisfies all my constraints, including those path constraints, and minimizes or maximizes, depending upon what I'm doing, that objective function, right? So it doesn't know anything about this constraint any differently from any of these other constraints, with one exception. This gets into the details of nonlinear programming, which is a little bit beyond this class, which is that these are equality constraints, and there's actually TF minus T0 over 2 in front of this whole thing. But these are equality constraints, right? And that's an inequality constraint. The difference between the way this would get treated and the way that would get treated is snop or fmin-con or any other NLP solver knows that this constraint has to be binding at the optimal solution because you've told it it's an equality constraint, right? Given the fact that it's an equality, it's going to say, well, whatever it is I do, I have to satisfy this constraint at the end. In the process of doing this, it has to determine whether or not the constraint is going to be binding at any point along the trajectory. Right? And there's no trajectory at any point in this discrete space, right? It doesn't know ahead of time. So the NLP solver method is going to determine it. There are all kinds of methods that are used for nonlinear programming. There are active set methods, there are interior point methods. That's all really beyond the scope of this class. But the point is that those techniques will actually determine for you whether or not a constraint is actually binding at the optimal solution or whether it's not binding. But from your perspective, when you actually solve the problem, you don't need to know any of that stuff. You don't need to know whether it's binding or not. You just need to tell the NLP solver, here's the constraint I want you to satisfy. Go ahead and find a solution to this problem. Now, look at how much, so you look at these two things, and they're quite disparate from one another, right? The theory says that I got to go through all these conundrums to figure out whether or not the constraint is active, what the arcs are that it's active over. There's a lot of stuff. I got these tangency conditions. There are all kinds of stuff that needs to be done. Over here, I don't need to know any of this stuff. Now, if you're a naive person, you'll say, okay, well, I'll formulate this NLP. I'll send it to the NLP solver. It's going to come back and give me some solution, right? And I'm going to say, voila, I'm done, right? And I'm going to say, no, you're not. I'm going to say, you just got started. Because you just got started, meaning you solved this problem, or you solved the problem you think you solved, right? That's even worse, right? You think you put a particular problem in, and then you get some solution back, and the naive person says, hey, you know what? It says I found an optimal solution. And you're like, oh, I'm great. This is awesome. I'm done, right? And I say, well, how do you know you even got the solution to the problem you thought you solved? Maybe you coded this function wrong. How do you know you didn't code the function wrong? Now let's assume you've coded the function right. How do you know when you're all done if these constraints happen to be active at some points? How do you know whether or not they're actually correct? So now what you do is you bridge the gap and you go back to the theory. And you say, well, do these constraints, if they're active, satisfy what I know has to be true in the theory, right? Because if it doesn't, you don't have the right solution. Even though the NLP solver may say, hey, you know what? I found a solution for you. It may not be the right solution because it may not satisfy, to some reasonable approximation, these conditions that you know have to be true, right? So you can't just naively say, oh, I threw this thing to an NLP solver. It gave me back some trajectory, because it did not give you back a trajectory. It gave you back a bunch of discrete points. That's all it gave you back, right? It said I got this giant NLP decision vector, and that's my decision vector. It doesn't know anything about any one of those components of the decision vector any more than it knows about any other component of the decision vector. It's a big vector Z. And for all it cares, that vector Z could have come from Mars, Venus, Pluto, or it could have come from an optimal control problem, right? It doesn't know anything about your optimal control problem. It knows that you gave it a bunch of equations that need to be solved. That's all it knows, nothing more than that. It's your job as the person who actually is an expert in the subject of optimal control to say, I'm not satisfied with the NLP solver coming back and giving me a solution. I need to do some analysis to check whether or not what I got actually makes any sense. the analysis that needs to be done has to go back to what the basic theory tells you. Now, clearly, if I solve this problem, I'm not going to satisfy any of these conditions exactly because, first of all, I made an approximation to get that NLP to begin with, right? This NLP came from an approximation of the optimal control problem. So that begs the question, is the approximation that you made a reasonable approximation? The only way you're going to be able to figure that out is if you go back in and you check to see whether or not your function approximations, when you actually stuff those function approximations back into all this theory, whether or not it makes any sense, right? I've approximated the state with some polynomial. How do I know that that polynomial approximation is any good? That polynomial approximation could be terrible for all I know, right? So you have to know something about what the basic theory tells you in order to be able to relate this nice formulation that you get with this NLP, because with the NLP, you don't have to worry about all these tangency conditions when you formulate the problem, right? Problem formulation doesn't require you to do any of this stuff. But when you're all done, you now need to relate it back to what you know has to be true at the optimal solution. So what you're going to find here is you're going to get back a bunch of discrete points. And there may be some values of this function for which you get that the constraint is actually active. So here's what it might look like when you're all done. You might actually get something that looks like this. Because remember, you're not getting back a function of time. There's no function of time in here. There are a bunch of discrete points. So what you might get back is something that looks like this. Here's t0. Well, here's the initial point, and here's the final point, right? So if I label these 1, and I label this n plus 1, which is my final Redal point, I may get a value of c here. I'll get a value of c here. Get a value of c here. Something here. And remember, I'm not collocating at the final point. And here, maybe the value is 0. Okay? There's 0. There's c. Now, what this does not tell me, it does not tell me that the constraint is active between here and here. That is not what it tells me. What it tells me is these are 2 points in the discrete approximation for which those discrete constraints are binding. That's all it tells me, right? Because this is not a function of time. This is a function of my Redal points, right? Because all I've done here is I've discretized at these points. So what I have to do now is I have to go back in and I've got to say, well, what was my state approximation? I had some polynomial I used to approximate the state. What was my control approximation? Well, herein lies the problem. You remember when I derived these methods, I never actually approximated the control with a function, right? There is no unique function approximation for the control. There's a unique function approximation for the state, because when I started with the state approximation, I differentiated it and then did the collocation on the derivative, right? I never did that for the control. So the control doesn't have any kind of function approximation. So herein lies a big issue. What do I use to interpolate the control? Because I have the control at these Redal points, but I don't have a function approximation. So any function that passes through these points satisfies my constraints in the discrete problem, right? So therein lies an issue. So you have to experiment with this a little bit. You have to say, well, if I use a spline approximation for the control, here's what it's going to look like. If I use a linear approximation for the control, here's what it's going to look like. And it may turn out that actually, when you fit a curve through this, depending upon what approximation you use, you may get something that looks like this. Nothing that says that it's not going to violate the constraints in between, right? So just because it satisfies the constraint here and there doesn't mean that even in between my approximation is going to be binding, is going to be at the boundary of the constraint, and it may be that whatever polynomial I use actually goes above the constraint. So is this a good approximation? If I drew that there, would that be a good approximation? No, it wouldn't. Now you'd say, well, that's not a very good approximation because I know my constraint's violated here on the interpolated solution based on whatever functions I'm using to interpolate the state, right? In the case of the state and control. In the case of the state, I'm using this Lagrange polynomial. In the case of the control, I've got to figure out what it is I'm using. Depending upon what I use, I'm going to get a different value for these points in between the collocation points. So this is not, the upshot of this lecture is I've got some conditions over here that I can use in simple problems to be able to determine activity or inactivity of a path constraint. But in reality, I need to have something that's more general that will allow me to be able to do it when I don't know anything about the structure, right? But once I do that, I have a ton of analysis that I need to do in order to make sure that, yes, in fact, what I'm getting is reasonable. And reasonable has to do with, does it match the theory? And if it doesn't, how much is it off? Right? In this case, you could tell that if I use some function approximation for the control, and I use that Lagrange polynomial approximation for the state, this is how much my approximation tells me I'm off, right? Because I know that C has to be less than or equal to 0, but in these regions right here, my function approximation actually violates the constraint. So what I would have to do, or what I might do, is increase the number of collocation points and solve it again, and to see if I can reduce that discrepancy between what I know has to be true and what is actually true on the approximation. And when that comes to within some tolerance, I say, okay, now my approximation is good enough. Okay? So we're going to stop with that today. So that covers my stuff on inequality constraints. What we're going to do next is I got this question that came up about feedback and optimal control and being able to use optimal control in like solutions to optimal control problems for like, for doing inner loop control. So we're going to talk a little bit next week about this concept of neighboring optimal control and how you actually linearize about the optimal solutions and what you get and how you can actually use that in a feedback sense, all right? And then what I'm going to do is I'm going to talk about dynamic programming. I haven't talked about dynamic programming yet. We're going to talk about the Hamilton-Jacobi-Bellman equation, and we're going to talk about dynamic programming. That's the last big topic in this class. We're going to spend a little time